So I think we can start now. Okay. Well, uh, today we'll discuss three articles. So today's a small reading club. Two of them is about optimizers. So and some some investigations of the learning neural networks, optimizing neuron, and reasoning in a large language model, so in latent space, continuous latent space. So let's start with the Broking paper. Well, so this paper explores an interesting phenomenon in a neural network. So, like training in training process. So where sometimes some models first overfit the training data, but later grok, suddenly understand the underlying pattern. So I think so, leading to great and good improvement in generalization performance. So this behavior occurs long after the model has achieved great, I think sometimes perfect accuracy on the training set, and sometimes it's there can be some challenge in classical notions with the learning theory. So first of all, I think we can discuss what is groking. So the definition of groking something, so comes from Robert Heinlein's science. It's a novel Stranger in a Strange Land. So, and groking, so it means to deeply understand something intuitively or suddenly, for example, grasp a concept. So, in this context, it refers to some situations where a neural network can initially memorize the training data and performs poorly on the validation data. For example, so it's like overfits, of course. So, but then after further training, its validation accuracy suddenly jumps. Yes, so here you can see in this image. So suddenly, from a random chance to near perfect generalization. So, this is the effect. So, this phenomenon shows that overfitting is not always the end of learning. So we can continue. We can continue it, and maybe in the future, our large language model neural network will have great, perfect accuracy. So, and the second one is generalization can improve significantly even after the model has fully overfit the training data. So, if we talk about the experimental setup or method, yes, so the authors used small algorithmically generated data sets, specifically binary operation tables of the form like A, B, and C. So, and like a separate token. Okay, we can see here in the appendix. So as you can see here, this is the binary or binary operations. So for each binary operation, they construct or the form like this. Yes, and this is the corresponding token to the element. So this is these, for example, let's turn back. These tokens, for example, A, B, C. This is the discrete symbols. For example, numbers like modulo 97, for example. Yes, and this token, like a dot, in multiplication, division, or something else. So each number was created as a unique token, so with no internal structure. For example, not represented numerically. So we're forcing the model to learn relationships purely from interactions between tokens. So some examples of operations can include something, for example, yes, as you can see here, yes, so, or here, maybe something else, more like this. So, and so the data set so it's in data set we have to solve in Sudoku puzzle like this, given some entries in a table, and so well, this is here you can small binary operation table. So yes, and so the model have to fill the blanks. The model architecture, which they created, so I can find here. Sorry. Maybe it's an appendix. Yes, model and optimization. So yes, so model. So it's a decoder-only transformer with 2 layers, 4 attention heads, embedding size 128. So and a total about 400,000 parameters, of course excluding embeddings. And they trained using Adam V optimizer, unless otherwise specified. What about results? So you can find something. Well, some training accuracy reaches nearly 100% within 1,000 optimization steps. This is, for example, one point. Random chance level, about 1%. So I can find here something else. Okay. Well, yeah. And relation accuracy rapidly improves, reaching 100% by about 1 million steps. So these findings and they suggest that the model first memorizes and only later discovers the underlying algorithmic patterns. from the data. So, well, some effects on the data sets we can see. So the smaller the training data sets, the more optimization steps are needed for a generalization. So the main idea that if you have some small data set or not, we otherwise we can make generalization from the neural network, but sometimes you have to do so many validation steps and training steps. So about, for example, 1 million. You got overfitting at the beginning of the learning neural network. So, but um, so in the continuous process, after 1 million steps, you can got generalization, and this is incredible result. This is a great result, which can help so many companies in industry to train, not cancel some training processes of the network, and we can save compute resources, of course, in some situations. But of course, we have to notice that 1 million training steps, that's a lot. It's a lot in computer resources. So, and so the another point, when trained on only 30% of the full data set, reducing the training data by 1% can increase the required steps for generalization for 40 or 50%. So it's about here. So yes. Well, what about weight decay and some data efficiency? And on several regularization techniques, which were tested in this article, for example, dropout, gradient noise, learning rate variations. So weight decay had the most significant effect. So it's great results, great result. So, and we can use it in our work or our education. So and weight decay toward zero, not just toward initial values, so was particularly effective, suggesting that fairer and simpler solutions helps generalization. So weight decay is a great realization technique which we can use in our work. So and one more point, as I remember, so it was a double descent curve in validation loss. Maybe I can find it. Okay, so maybe I can find just here it is. Yes, this is the double descent validation loss. So they discuss it well, and one. Okay, so it's here. Double descent curve in evaluation loss is like a function of the training steps. So after initial overfitting, where evaluation loss increases, the model eventually escapes the sharp minimum and finds some flatter region of the loss landscape, improving generalization. So We can here, I think it's interesting for some scientists that this concept can, can so do some broader work. So on a deep double descent, where increasing model size or training time can lead to better generalization after initial degradation. So why this work is interesting and why I want to show you this grokking generalization overfitting on small algorithmic datasets. So this work provides a controlled environment to study how deep learning models generalize beyond mere memorization. So it reveals that, first of all, neural networks can transition from memorization to understanding. It's a vital fact. So first of all, the second one, regularization and extended training are key to this process, and the loss landscape plays a role. So flatter minima correlate with a better generalization. So, and I think these insights challenge some traditional machine learning assumptions and suggest new ways to think about some optimization dynamics, simplistic realization, some knowledge structure, etc. So, and now we can discuss this visualization. So the authors visualized the embedding space of the output layer using TSNE. Not a great solution for visualization, but okay. So, so they found that, they found that first of all, models trained with the weight decay showed clear topological structures. For example, circular patterns for a model arithmetic. So as you can see, yes, here, for example, it's the right place. Yes. So and these structures, they reflected the mathematical properties of the operations. So some, for example, causes in group theory. So, and it's great. So, because using neural networks to discover hidden structures in mathematical objects, we can use it. So, and we can do some research on it. And I think gaining intuition about abstract algebraic systems through learned representations, we can do it also too. So, was a small work, leading to grokking. So now it was like a optimizer work, optimization, and a bit regularization, and some interesting facts of uh, knowledge structure of the neural network. So, and now we will move to Muon optimizer, which accelerates grokking. So this is why we discussed grokking theory or the previous step, and now we will discuss this paper from the Microsoft. So, and this paper investigates how the choice of optimizer affects the phenomenon like a grokking, the grokking phenomenon, so which we discussed now. So, and in this, okay, this, we know this, in this phenomenon, we model initially learns to memorize training data and performs poorly on the validation, but then suddenly transitions to great regularization after further training. So, and here we can see Muon optimizer, which incorporates second order optimization principles and some spectral norm constraints, significantly accelerates this transition compared to the widely used ADAM-W. So, well, I don't want to see some grokking effects because we've just discussed it. I think in this paper this was really interesting. Grokking is defined operationally. So the first epoch when validation accuracy reaches or exceeds 95%, after training, accuracy has stabilized near 100%. So this is the definition of grokking, and it's great because in the previous paper we discussed grokking a lot, but we didn't find some definitions of it. So, and the researchers, so they experimental stop. So yes, so the same problem. Yes, so they tested some 7 algorithmic tasks, modular arithmetic operations, some addition, multiplication, some division, exponential, modulo 97, for example. Yes, great common divisor. So here, okay, I lost it. I lost this. Okay, so otherwise, and of course the third one, binary parity check for 10 bits numbers. So here it is. Each dataset contains all possible input-output pairs. For example, combination. For example, like about 94,000, about 94, 9,000 combinations for mod 97 tasks. So a random subset was used for training. The rest were reserved for validation. So it is the simple data structure. Yes, experimental setup. So, and what about model architecture? So model architecture is a transformer based architecture with some identity embeddings. So with token 42 maps to vector 42. Yes, they used rotary position embeddings. Okay, here it is. So they use normalization, RMS norm, SILU activation function. So like a segment linear unit. If you don't know how it looks like, here it is. SILU a bit. So a bit. We have here some negative values after the 0, on the left of the 0. Then we don't have the linear linear growth. So here, okay. Okay, some dropout regularization, residual connections, so etc. Some here we can see some multi-head attention, transformer blocks, standard transformer. So, and which optimizer they compared? So it's ADAM-W with some hyperparameters and Muon. Muon, it's a recent optimizer. So which uses spectral norm constraints, some second order information approximation, like a Newton-Schulz iterations. Some we can read about Muon more if you want. So, and orthogonalized gradient updates. So importantly, Muon is designed to optimize only more than 2D parameters, so like weight matrices. So while embeddings, scale parameters, and classifications heads are typically trained using ADAM-W. These authors has some softmax variants tested. They tested the standard softmax function, stable max. It's improved the numerical stability, as you can see. Yes, it's here, and sparse max. So this function encourages some sparsity in outputs. So that's all. Okay, so what are the key findings of the experimental setup and experimental results. So first of all, Muon uh, Muon dramatically speeds up grokking. So it's accelerates really great. Um, mean grokking epoch of the Adam W. It's a 153 in the mean grokking epoch. So when as you can see, so it's the definition of grokking. So when we have on the train set 100% accuracy and the validation set more than 95%. So and a mean grokking epoch muon it's about 100. So it's great and. Statistical significance is great too. So we have a t-statistical like a 5 point, so 175, and here we have a really small p-value. So this result shows that muon consistently leads the earlier onset and generalization across some multiply tasks and configurations. So and the distribution of grokking times, I think we can see. Okay, see, here it is. So the distribution we, so they it's tighter. It's tighter for muon, indicating more reliable behavior. So as you can see, it's great. So and but why? And so the great question is why muon help. So the authors here we can see only hypothesis of the working results of the muon. Okay, here so it's an article. Um, uh, okay. Mm, so I think so. First of all, they have some broader exploration. So muon uses orthogonalized gradient updates. So and it helps to escape local minima and discover real patterns instead of memorizing. It prevents runaway weights. So because muon applies spectral norm constraints and it prevents weight explosion and avoids issues like softmax collapse. And some others, so like layer synchronization, better update directions, computational efficiency. So all of these, so muons matches update size to layer shape, approximates second order updates, and reduces flops per loss unit. And of course, all of these uh, features they ensures all parts, for example, of the network learn at balance rates. The muons reach generalization faster by following more accurate directions, and of course, muon enables grokking with less compute. So I think these characteristics help steer the model away from pure memorization earlier and allowing to find generalizable solutions sooner. Well, yes. So this is was the optimizer, which accelerates grokking in neural network. Well, so if you have some questions on these two works, so I think you can ask me about grokking effect and muon optimizer. 3 to 1. Okay, so let's discuss the last last article. It's about training a large language model for reasoning in a continuous latent space. It's a bit for me it was a bit harder. So, but I think so we'll do it. So it's the Meta company. I'm sorry. So if you want to ask me, so you can do it. So, but I don't hear you very well. It's a bit quiet, quiet. Uh, okay. Ah, okay, okay, okay. So no problem. Well, so the last paper. So this article introduces coconut. So it's the coconut. It's a chain of continuous thought. So it's a novel approach for reasoning in large language models by operating in a continuous latent space rather than in traditional language or language token space. So, and the authors used chain of thought methods so for this task. The authors argue that reasoning within the constraints of natural language may not be optimal, and Cognite aims to overcome these limitations by allowing large language models to reason more freely and efficiently. Uh, some summary of problem. Some summary of a problem. Traditional chain of thought reasoning forces large language models to express some logical steps uh, using human readable tokens. So like a text or a number, so etc. But so these can be inefficient because many tokens are redundant. So while others require complex planning. And here the idea, so Coconut bypasses this by using the last hidden state of the model as a continuous thought. So an embedding representing the current reasoning state. So this continuous thought is directly fed back into the model as input, enabling latent space reasoning without decoding into tokens. And Coconut so what's the result? So Coconut shows improved performance on some certain reasoning tasks with fewer generated tokens, suggesting it's better suited for complex search intensive reasoning. Um, was some summary. Here we can see chain of thought, chain of continuous thought, like a coconut, yes, as you can see. Um, but the main question is why move reasoning out of language space? So language doesn't equal reasoning. So neuroimaging studies for the brain, they they show that language areas of the brain are largely inactive during reasoning. And human language evolved primarily for a communication, not internal reasoning. We just for a I think you can understand this. So in some examples, uh, like if uh, somebody uh, stuck in an island without any uh, humans, the language, his language will be bad, will be worse as it was. It was before this stage, for this moment. And small children, when they grows, when they grow, so they analyze the language which is around them. For example, if you bring, for example, a Chinese child to the inland in a small age, and so you will grow it, yes, there, and speak with him only in English. So even if he doesn't know English, so he will learn it. So this is the neuroimaging studies. So the human language, our language, can evolve primarily in communication. So we don't speak with ourselves, so in our brain, in our thoughts, not reasoning, not internal reasoning. We just improve our language in communication and sometimes in reading. So, but therefore, forcing large language models to use natural language for reasoning may be suboptimal and not really effective. And second, token level limitations. So, okay, so it's here. In chain of thought, each token gets roughly the same computational budget, but some reasoning steps are much harder than others. So most tokens in chain of thought chains are for fluency or coherence, not actual reasoning, just improving the context. So, and some critical tokens like decision points, yes. So they are hard to generate accurately due to limited lockhead. So this is the token level limitations, which is the concept of the problem. And the third one is a latent space potential. So hidden representations in transformers, so already encode meaningful computations. So it is already encoded. And prior work, some prior work, we can discuss it. So here in related work, so it's here. For example, yes. So the latent reasoning as a hidden computation in transformers is constructed a dataset of two-hop reasoning problems and discovered that it's possible to recover the intermediate variable from the hidden representations. So intermediate variables. So intermediate variables can be recovered from hidden states. And the method of coconut, yes, chain of continuous thought, explores whether direct manipulation of hidden states can improve reasoning. And the key idea of coconut, this chain of continuous thought, instead of generating tokens step by step, so here, method in the method overview, I think it's like here it is. Yes. So instead of generating tokens, like Coconut uses the last hidden state. So we use only the last hidden state here, yes, and um, uh, and the coconut from the transformer, this last hidden state uses as a continuous thought, which is then used as the next input embedding. So how it works? So at each step, uh, instead of decoding the hidden state into a token, Coconut feeds it directly back into the model. And this creates a looped chain of continuous thoughts, similar to how chain of thought loops back generated tokens. So here, not it's a great image here. So we use on the last hidden state, I use like an input embedding. So and for model operations, which so It's I don't really remember, so it's we use them standard autoregressive generation, something like this. Some special tokens like a board. We can find it here. So I'm sorry, this article was extremely yes, here it is. Extremely harder than to another. So and this is the special tokens, so they mark the beginning and the end of the latent mode. So let's move to experiments. So yes, and some reasoning tasks and training dataset source. So a calculator is trained using existing chain of thought reasoning chains as a supervision. Yes, so it's the dataset and a multi-stage curriculum learning strategy is used to gradually replace language-based reasoning steps with continuous ones. So, and these multi-stage curriculum learning. So I should second multi. Um, I want to explain it detailed. Maybe it in appendix. Maybe just multi stage. So curriculum. Here it is. So yes, it's in appendix, I think. Oh no, it's in results and discussion. Okay, so yes, multi-stage curriculum. It on the initial stage, model learns to generate standard chain of thought. Intermediate in intermediate stages, first, for example, k steps of the chain of thought are replaced with a k multiplied by c continuous thoughts. So where c is a hyperparameter. Well, and the final stage, all chain of thought steps are replaced with a continuous thoughts. Yes, and between stages, the optimizer state is reset to avoid overfitting. So that's, for example, this is this one. Yes, yeah. As you can see, so reasoning process here we can see some k. Yes, so understandable. So we use less hallucinations, less incorrect label, etc. So, well, so about about um, about some results, I think. So we can move to them. Mhm. Oh, mhm. I found it. Okay, so of course the chain of thought, so chain of thought and no chain of thought, and this method. So as you can see, so it's really here the authors got incredible improvement in correct answers and the accuracy on the final answer and reasoning process as a baseline. So it's of course it's have the great values and the perfect results. Some key findings. So first of all, it's so if we chaining continuous thoughts improves performance. So it's like a chain of thought. So chaining increases effective model depth, and Coconut improves or some post token baselines and matches chain of thought on math text. Second one, so it's the latent reasoning excels in a complex planning tasks. For example, in a pros QA, just found it. It's not top. Okay, oh, here it is. Pros QA. In a pros QA, Coconut significantly outperforms chain of thought, as you can see here, and Coconut enables breadth first search. So like a behavior. So, and continued thoughts can represent multiple possible next steps. It's great findings. And the last one, the latent reasoning can be interpreted as a search trees. So it's like here, yes. Coconut's continuous thoughts can be decoded into some plausible language tokens, and these often correspond to intermediate reasoning variables. And multiple candidates are encoded in the vector, allowing the model to explore several reasoning paths at once. So, the last question is why latent space better for playing? So, first of all, Coconut assigns probabilities to different reasoning paths. Nodes closer to leaf nodes, so with less branching, and they have higher confidence scores. And Coconut performs a kind of implicit BFS, like breadth first search, with prioritization. And here we can see some parallelism in latent research and analysis of the top K candidate node. Probability shows the high diversity early on, so it's great results. As a reasoning progress, uncertainty, we suggest increasing certainty, so it's great. Well, like a conclusion, so Coconut reduces reliance on language tokens for reasoning and enables more efficient, flexible, and parallelizable reasoning, matches or some exceeds chain of thought performance with fewer tokens, and emergent behaviors resemble advanced reasoning patterns like breadth find search. So, well, such work. So I think it's really great for nowadays. Great article and great research. Real deep research. And it is great for use, I think, sometimes in a reasoning reasoning work. I think like a training neural network. This continuous thoughts like a Coconut. Well, so I shared the links of all these 3 articles with you. Now I think that's all for today. If you have some questions during the articles, so first, second, or third, you can ask me. Well, but for today, I think that's all.
Do we have a class next week?
I think now I think yes, but if something will change, I will write you, of course, too, because so it will be so it was strange to the teaching office that they said so today it's no practice, like only reading club seminar. So I had these 3 articles. So and I found them interesting and great for industry and for science, for academy. Well, and I wanted to discuss them with you. Well, I don't exactly know whether we will be the lesson the next week, but I think yes. Well, that's all for today. Thank you so much for this center, for this time. So I really wish you a great week and a good evening. Goodbye.
Thank you.